When we say the word dielectric, we are referring to materials which contain charges, but they are fixed or bound charges. For example, marble is a dielectric, leather is a dielectric. These materials, just like plastics and ceramics, do contain charges. They have molecules and atoms, but those charges are not able to move outside of those molecules or atoms. So dielectrics are not able to conduct electricity the way conductors can. Now, when we apply an external field, a static external field to a metal, it will react in a very different way compared to what happens when you apply a static electrical field to a dielectric material. Let us see what this difference is. So here we have a block of metal, and this metal contains free charges, right? It contains electrons which are mobile. We apply an external field to this metal. So here is our external field. Let's call it E0. And because of this external field, this field has a positive end. So here is our positive end. And this field has a negative end. So here is our negative end. Due to the presence of free electrons inside this conductor, what will happen? By sensing the positive end of the electrical field, the electrons will start drifting towards one side. So the free electrons inside this material, will all start drifting in one direction. And because they are drifting in one direction, a lot of positive charges will be uncovered in the other direction. So we will have positive charges being uncovered inside this material in the other direction. So we have an external field. This external field caused the drift of electrons and positive ions to opposite sides. Yes, positive ions don't move, but it seems as if they are moving due to the opposite motion of electrons. And as a result, we will see an internal induced field inside this metal, because what we have here is an imbalance in the distribution of charges inside the metal, and this internal field is what we will call EI. This is the induced field in this metal due to the presence of the external field, that is EO. Now in metals, this process of electron drift will happen until the external field is as strong as the induced field. Now in metals, this drift of electrons and positive charges to opposite sides will keep on happening until enough charge has accumulated to create an electrical field which can perfectly cancel out the external field. Thus, EI will keep on increasing. The induced field inside this material, which is opposing the external field, will keep on increasing to the point where EO and EI become equal and cancel each other out. So as a result, what you will see is that there is no internal field, there is no internal electrical field inside this material. Things happen very differently in the case of dielectrics. Now, before we pursue this subject of dielectrics, let's understand what is the meaning of polar and non-polar dielectrics. So what is the difference between a polar dielectric and a non-polar dielectric? If you look at the molecular behavior of materials, you will see that certain materials at the molecular level have an innate or built-in distribution of charges which is not symmetrical. For example, if you look at a molecule of sodium chloride, you will observe that sodium has a partial positive charge on it, and the chlorine atom also has a partial negative charge on it. So if you look at this molecule, it does have the behavior of a dipole. You are seeing a separation of positive and negative charges with some distance between them. Contrast this with the structure of something like CO2. So you have a carbon atom, you have two oxygen atoms surrounding it, and there is no imbalance of charge in this system. All the electrons between the carbon and oxygen atoms are being shared equally. So there is no asymmetry in the system. You have a uniform distribution of charges everywhere. So this material, carbon dioxide, is non-polar. It has no inbuilt dipole moment. On the other hand, materials like NaCl or the much more common material water, for example, if you look at the structure of water, you have two hydrogen atoms, each of which carry a partial positive charge, and you have an oxygen atom which carries a partial negative charge. Materials like salt, materials like water have a built-in dipole moment due to the asymmetric distribution of charge inside their molecules. These materials are what we call polar materials or polar molecules, while materials like CO2, hydrogen, most hydrocarbons are what we call non-polar materials. Now, why is this important? This is important because it helps us to understand what is happening in a dielectric material when we apply an electrical field to it. Let's see how this works. Consider a slab of dielectric material. So here we have a slab of dielectric material. So it contains no free charges. So here is our dielectric. All the charges inside are fixed to the parent atoms or parent molecules. We apply an external field here. So here is our external field in this direction. Remember, we are dealing with a non-polar dielectric, so there is no inherent dipole moment, there is no inherent imbalance of charge inside this material. When we apply this external field, let's call it E naught, it will cause some kind of strain inside these molecules and atoms, because while the electrons inside this material cannot actually leave their atom or molecule and move towards the positive end of the field, they will feel the force caused by the electrical field. Conversely, the nucleus is positively charged, so it will feel an attraction towards the negative end of the field. And as a result, these molecules, which were hitherto undistorted, will start stretching out a little. So we will notice that there is a stretch in these molecules. So they start looking something like this. They start stretching out from their normal equilibrium and they have a distorted appearance. And because of this distortion, there is an imbalance of charge on the hole in this material. So we will start observing some distortion in the molecular makeup of this material. The molecules will be deforming or distorting under the influence of the external field. Remember, the positively charged nuclei are feeling the effect of the attraction from the negative end of the electrical field. So here we have the negative end of the field to which the positive nuclei are being attracted. So there will be a slight shift in their position with respect to their parent molecules, while the electron clouds inside these molecules or atoms will be feeling the attraction of the positive end of the electrical field. So the distortion will cause them to drift towards the opposite side of the molecules. If the external field is removed, the distorting effect on these molecules goes away and they will collapse back to their normal equilibrium positions. This is what is happening inside a non-polar dielectric material. What happens inside a polar material? Let's see. So here we have a polar dielectric. As you can see, the picture is slightly different here. Instead of having atoms in which the charges are uniformly distributed inside the material, here we have an imbalance inside each atom or molecule. We have the migration of charges towards one side of the molecule. So we have a concentration of negative charges on one side and positive charges on the other side. The dielectric materials which are classified as polar will develop a overall dipole moment for the entire material or a polarization for the entire material. But the mechanism for this happening is slightly different from what happens in non-polar dielectrics. What is happening is that if you take any polar dielectric and it is in the absence of an electrical field, all the different molecules inside the material will be oriented in random directions. So even though each molecule by itself has a definite dipole moment, because of the fact that all of these dipoles are randomly arranged, the net dipole moment or polarization of this material will still be zero. The picture changes when you apply an external field. When you apply an external field, this is what will happen. Under the influence of the external field, the individual molecules will try to rearrange to align themselves in a anti-parallel or parallel direction with the external field. So in this case, the net polarization of the material will depend on how well the individual molecules are able to align with the external field. In fact, we can define this mathematically as a quantity called polarization. So we can define this as polarization, which is denoted by the symbol P, and this polarization for these materials is equal to this symbol multiplied by the external field. So what is this symbol? This symbol stands for electrical susceptibility of a dielectric material. The higher the value of electrical susceptibility, the more easily the individual dipoles, the individual molecules are able to align with the external field. When you apply an external electrical field to a dielectric, it is causing an imbalance of charge inside the material. However, since these charges are not mobile, they can't move from one place to the other, the amount of the reverse induced field in a dielectric will never be the same as the external field. So there will be some unbalanced charges existing on both sides of the dielectric, which means that if you are applying an electrical field to a dielectric, you will achieve some kind of charge density on both sides. So on the negative side of the external field, you will have a positive charge density sigma p, and on the positive side of the external field, you will see a negative charge density, negative sigma p on the surface of the material. So by applying an external field to a dielectric material, you can achieve a surface charge density on the outside of this material, which is oriented in the opposite direction of the external field.
Manorama Horizon. Learning made simple.